Hello there, and welcome to Physics Before Bed. Before we drift off together into the mysteries of the universe, make sure to like this video and subscribe so you don't miss any of our gentle journeys through space, time, and science. Now, I'm curious. Where are you watching or listening from tonight? Perhaps your room, a cozy corner of a library, or maybe even somewhere far away under the stars. It's a small but fascinating thought, because as we explore gravity tonight, we'll discover that where you are and how mass and energy curve the space around you matters more than you might ever imagine. Tonight, we're going to rethink something that feels so familiar it's almost invisible: gravity. We've been taught since childhood that it's a force pulling us down, keeping our feet on the floor, making apples fall from trees, and holding planets in orbit. But what if I told you that this common understanding is only part of the story? What if gravity isn't really a force at all? Not in the way you might imagine from pushing, pulling, or tugging. In the next journey together, we'll move from Newton's apple and the clockwork universe to Einstein's revolutionary ideas of curved space-time, and even further into the strange and elegant worlds of quantum theory, emergent gravity, and the cutting-edge experiments probing the unseen geometry of our cosmos. We'll meet not just the familiar names, but also some brilliant minds you may not have heard of, whose work challenges and stretches the very boundaries of how we understand the universe. So settle in, get comfortable, and let's slowly explore why gravity is far more mysterious, intricate, and beautiful than a simple force pulling downward, and why the very fabric of reality itself bends and curves in ways that leave even the most seasoned scientists in awe. By the end of this journey, you may never think about falling, floating, or even standing in quite the same way again. Hello and welcome to The Sleepy Scientist. Tonight, before we ease into the quiet vastness of the universe, make sure to like this video and subscribe so you can drift with us through these gentle explorations again and again. I wonder where you are listening from this evening. Perhaps under a blanket with a cup of tea, or maybe in a room where the faint hum of the city reaches you softly. It is a simple thought, yet when you consider gravity, even that small notion of location takes on a profound significance, because space, time, and mass are more connected than they first appear. Gravity is often taught as a force, a pull that drags us downward and keeps the planets tracing their stately paths around the sun. We're told it is universal, invisible, and predictable, acting on everything equally. And yet, while that description is useful, it hides a deeper truth. Gravity, as modern physics reveals, is not a force in the conventional sense. It is an emergent property of space-time itself, the gentle curvature of the four-dimensional fabric in which all matter and energy exist. Instead of imagining a mysterious hand pulling on every object, think of planets and stars gliding along curved paths like tiny boats drifting along the waves of a vast invisible ocean. The universe does not tug at them. It shapes the terrain, and their motion follows naturally. Our intuition, honed in a world of tables and chairs, floors and ceilings, struggles to grasp this. We live in an environment where we experience gravity constantly, and we learn to think of it as a force, pushing or pulling in the simplest way. Isaac Newton's apple may have fallen on his head and revealed a regularity of motion that seemed miraculous. Yet even Newton recognized the limitations of this view. He described the gravitational attraction mathematically in what we now call Newton's law of universal gravitation, a simple formula in which the force between two objects depends on their masses, divided by the square of the distance between them. It works wonderfully for objects on Earth, for the Moon orbiting the Earth, and for the planets circling the Sun. It is elegant, predictive, and profoundly useful. But as the 19th century waned and the 20th emerged, cracks in this neat framework began to show. Light did not behave as expected near massive objects, and the idea of instantaneous action at a distance, where one body influences another across the void with no mediator, became increasingly uncomfortable for scientists who demanded a more complete understanding of nature. In the early 20th century, Albert Einstein offered that understanding, first with special relativity in 1905, then with general relativity in 1915. Here, gravity is recast not as a force acting across space, but as a curvature of space-time itself, a geometric effect produced by mass and energy. Massive objects like the Sun or Jupiter bend the space-time around them, and smaller objects follow paths dictated by that curvature. The planets do not feel a pull. They follow the straightest possible routes in a landscape that is subtly, invisibly bent. This is a subtle distinction, yet one that completely reshapes our conception of the universe. It turns the notion of gravity from an action into a property, from a tug into a contour, from a force into a form. Some of the foundations for this elegant view were laid decades earlier by Élie Cartan, a French mathematician who extended the ideas of differential geometry to include torsion, a kind of twisting of space-time that complements curvature. In Cartan's framework, the fabric of the cosmos is not simply a smooth stage on which events unfold, but a dynamic entity with geometric properties that can be bent, twisted, and warped. These ideas, while abstract, provide a bridge to modern explorations in both general relativity and theories of quantum gravity, reminding us that even the very stage of reality is active and responsive, not merely passive. The journey we are about to take moves gently through these layers of understanding. We will begin with the familiar classical mechanics of Newton, and slowly step into Einstein's revolutionary ideas of curved space-time. From there, we will explore the realm of quantum and emergent gravity, where space-time itself may arise from deeper microscopic processes, where information, entropy, and even the structure of reality at the tiniest scales influence the motion of stars and planets. Along the way, we will encounter scientists both famous and less widely known, thinkers whose insights challenge our assumptions and expand our imagination, from Carlo Rovelli and Lee Smolin exploring loop quantum gravity, to Ted Jacobson connecting Einstein's equations to thermodynamic principles. Even as we contemplate these profound ideas, the tone remains calm, reflective, and light, encouraging a sense of curiosity without pressure or strain. Imagine the universe as a gentle ocean, vast and unknowable in its entirety, yet revealing waves as patterns if one observes patiently. The curvature of space-time is one of these patterns, subtle, almost imperceptible in daily life, yet governing the majestic dance of galaxies and the fall of an apple alike. There is a beauty in realizing that the very phenomena we take for granted are manifestations of geometry and structure, and that our place in the cosmos is subtly determined by the invisible shapes of space and time. As we move forward, consider gravity not as a pull or a push, but as the shape and flow of space-time around every mass. The planets, the moon, the stars, and even ourselves are travellers following these invisible contours, moving with grace dictated by the curvature of the universe itself. This perspective reshapes not only physics, but the way we perceive our place in the cosmos. It invites us to contemplate a reality where the familiar becomes extraordinary, where the ordinary experience of standing, falling, or orbiting transforms into a meditation on geometry, motion, and connection. Let us breathe in that subtle wonder, embracing both the elegance and the strangeness of this view. The universe is not a collection of objects pushing and pulling on one another in empty space, but a rich tapestry of curves, twists, and flows. Gravity is the melody played on this cosmic fabric, and through it, we begin to see that the ordinary, the everyday, is a reflection of the extraordinary structure beneath. In this quiet contemplation, we find both understanding and serenity, the perfect beginning for a journey through the hidden architecture of reality. A journey that invites us to perceive the cosmos not just with our eyes, but with a deep, reflective awareness of the very shape of existence. When we first consider gravity, our minds often leap to Isaac Newton, the 17th century mathematician and physicist whose apple famously prompted contemplation of motion and force. Newton described gravity as a universal attraction between any two masses, a pull proportional to the product of their masses and inversely proportional to the square of the distance between them. In simple terms, if the distance between objects doubles, the gravitational effect drops to 1/4 of its original strength. This insight formed the backbone of classical mechanics, a framework so precise that it allowed engineers centuries later to calculate trajectories for ships, bridges, and eventually spacecraft, all without knowing the full nature of the underlying force. Newton's laws are elegant in their simplicity. They tell us that an object in motion stays in motion unless acted upon, that forces produce acceleration in direct proportion to mass, and that every action has an equal and opposite reaction. These laws work remarkably well for planets, moons, falling apples, and even the motions of tides, which are influenced by the gravitational pull of the moon on the oceans. Yet, as powerful as Newton's framework is, it is not complete. It assumes that space and time are fixed, absolute stages on which objects move, and that gravity acts instantaneously across any distance. For centuries this view served science well, but observations began to reveal its limitations. In the late 18th and early 19th centuries, Pierre-Simon Laplace approached gravity with a slightly different perspective. He considered the universe as a probabilistic system, contemplating that mass distributions might influence motion in subtle, statistically predictable ways. While Laplace never discarded Newton's laws, he encouraged thinking about the cosmos not just deterministically, but also in terms of probabilities and distributions, laying conceptual groundwork for later statistical mechanics, and for the idea that gravity might have a deeper underlying explanation. Another influential thinker was Ernst Mach, an Austrian physicist and philosopher who questioned the very notion of absolute space. Mach suggested that motion and inertia could only be understood in relation to other masses in the universe. In other words, a solitary object floating in an empty void would have no meaningful concept of movement or acceleration, because there would be nothing to compare it to. This idea, subtle yet profound, later inspired Albert Einstein as he formulated the equivalence principle, a cornerstone of general relativity. Mach reminded scientists that the relationships between matter, rather than absolute positions in space, might hold the key to understanding motion and gravity. Despite these challenges to classical thinking, Newton's laws remain astonishingly accurate for most situations encountered in daily life. They govern the orbits of planets in our solar system, the trajectory of a thrown ball, or the construction of a suspension bridge. Even when dealing with spacecraft, Newtonian physics is often sufficient, requiring only small relativistic corrections when velocities approach a significant fraction of the speed of light or when gravitational fields become extremely strong. In essence, Newton provides a highly effective approximation, a practical map of reality that works beautifully within its domain, even if it does not capture the deeper geometric and relativistic truths that lie beneath. When we examine Newtonian gravity closely, we notice that the force between two objects is described mathematically by the formula force equals the gravitational constant multiplied by the product of the two masses divided by the square of the distance between them. While this is simple and elegant, it implicitly assumes an invisible line connecting every object to every other object, transmitting influence instantly across space. This assumption, while serviceable for planets and apples, becomes problematic when light, time, and very massive objects are introduced into the equation. The idea of instantaneous action at a distance puzzled even Newton himself, who admitted that he could not conceive of the mechanism by which gravity acted. It is here that modern reinterpretations begin to illuminate the landscape. While we still use Newton's equations for practical calculations, we now understand that they are approximations of a more fundamental picture. Gravity, rather than being a mysterious pull, emerges from the curvature of space-time caused by mass and energy. The universe is not a stage with actors tugging on one another invisibly. It is a living geometric fabric, subtly shaped and bent by the presence of matter. Newton provided the rules for motion on a flat stage, and his genius lies in capturing the regularities we can measure. Yet the stage itself is far more intricate than he imagined, filled with curves, twists, and unseen depths that reveal themselves only when we look beyond the familiar. In revisiting Newton with a modern lens, we also appreciate the continuity of scientific progress. Classical mechanics, Laplace's probabilistic musings, and Mach's philosophical critiques all feed naturally into Einstein's revolutionary ideas of curved spacetime. These perspectives encourage us to see the universe not only in terms of objects and forces, but also in terms of relationships, geometry, and the flow of time itself. Even when we are simply standing on the floor, or watching the moon glide across the night sky, we are participating in the elegant dance of matter and geometry that Newton first glimpsed, and that modern physics continues to reveal in ever more subtle and astonishing ways. Through this calm reflection on Newton and the thinkers who questioned and expanded his work, we begin to glimpse a universe that is at once familiar and extraordinary, a place where gravity is more than a pull, a force, or a simple law. It is a window into the deeper, richer structure of reality itself. In contemplating motion and gravity, one encounters a subtle yet profound idea known as Mach's principle, named after the Austrian physicist and philosopher Ernst Mach. At its core, Mach's principle suggests that inertia, the resistance of an object to changes in its motion, is not an intrinsic property of that object alone, but rather a relational property arising from its interaction with the distribution of mass throughout the universe. In other words, a single object floating in an otherwise empty cosmos would have no meaningful notion of motion or acceleration, because there would be nothing against which to measure its state. Motion, according to this perspective, is always defined relative to other matter. Gravity and inertia, then, are not simply local phenomena. They are woven into the fabric of the cosmos itself, dependent on the totality of mass and energy in existence. The idea is both elegant and challenging. It shifts our perspective from thinking of objects as independent actors subjected to forces to seeing them as part of an intricate network of relationships that define their behavior. In practical terms, this principle hints that local motion is influenced by the distant stars, by galaxies far beyond our reach, and even by the faintest wisps of matter scattered across the observable universe. The implications are vast. It suggests that the very nature of acceleration, of falling, and of the resistance to motion is fundamentally tied to the cosmic environment, linking the smallest particle to the grand architecture of the cosmos. Modern interpretations of Mach's principle have been explored by physicists such as Julian Barber and Bruno Bertotti, who reimagine these ideas in the context of relational dynamics. Barber, in particular, has emphasized that space and time themselves may be emergent concepts arising from the relationships between objects, rather than absolute entities that exist independently. In collaboration with Bertotti, he developed models in which the dynamics of the system can be fully described by the relative distances and motions of its components, without reference to any external background space. This approach resonates with the notion that the universe is a self-contained, interdependent system, where local behavior cannot be divorced from the global distribution of matter. Observationally, the universe provides subtle hints that our motion is influenced by faraway mass. The cosmic microwave background, for example, gives us a reference frame relative to which our galaxy moves, allowing astronomers to detect our velocity through tiny variations in temperature across the sky. Similarly, the gravitational influence of massive structures like galaxy clusters affects the trajectories of other galaxies and light passing nearby, providing concrete evidence that matter is deeply interconnected across immense distances. These phenomena, while not direct measurements of Mach's principle, exemplify the relational nature of motion and gravity in the cosmos. Philosophically, Mach's ideas challenge centuries of thinking about space and motion. Where Newton had envisioned absolute space, a fixed stage on which objects move, Mach suggested that space has meaning only through the objects within it. This perspective foreshadowed the revolutionary step taken by Albert Einstein in formulating the equivalence principle and ultimately general relativity. In Einstein's geometric view of gravity, mass and energy do not act at a distance through some invisible tug. They curve space-time, and objects move along paths determined by this curvature. In a profound sense, Mach's insight into relational motion laid the conceptual foundation for understanding that the geometry of the cosmos dictates motion, linking the distribution of matter to the shape and flow of space-time itself. To imagine this more concretely, consider two astronauts drifting in deep space, far from any planet or star. If they were truly alone, spinning or moving would be meaningless. They would have no reference points to define motion. However, the presence of distant galaxies, the cosmic web of matter, and the structure of the universe provide the subtle, relational scaffolding that gives meaning to their motion. It is not that these distant stars exert a force in the Newtonian sense. Rather, their existence defines the relational framework in which inertia and gravity manifest locally. Motion is thus a conversation with the cosmos, a whisper of connection that stretches across unimaginable distances. Relational thinking also invites us to reconsider everyday phenomena from a fresh perspective. The resistance you feel when pushing a chair, the apparent weight of an object, or the pull of gravity on a falling apple, are all deeply tied to the global arrangement of mass in the universe. While Newton's equations provide an extraordinarily accurate local description, Mach's principle encourages us to see the underlying interdependence. reminding us that what appears simple and self-contained is, in reality, subtly connected to the cosmos at large. In the modern era, this perspective has inspired further theoretical developments. Relational gravity models, often discussed alongside emergent and quantum gravity theories, treat space-time and motion not as fundamental givens, but as consequences of deeper relational structures. This is particularly evident in attempts to quantize gravity, where the fundamental degrees of freedom are not points in space but networks of relationships, as seen in loop quantum gravity and other discrete approaches. Even here, Mach's insight resonates. The properties of objects arise from the ensemble of relations they participate in, rather than exist in independently. This relational view transforms how we conceptualize not just motion and gravity, but the very fabric of reality. It emphasizes that the universe is a coherent, interconnected system, where local phenomena are inseparable from the global context. While we may never directly measure the influence of every distant star on a single object, the consistency and predictive power of general relativity suggest that the universe behaves as if these connections matter, guiding the paths of planets, light, and even the faint ripples of space-time itself. As we reflect on Mach's principle and relational gravity, we begin to see the universe as a delicate, interconnected web. Gravity emerges not simply from masses pulling on one another, but from the relationships, distributions, and collective presence of all matter. It is a cosmic symphony, where each object plays its part in harmony with countless others, and where inertia and motion arise from the subtle, invisible geometry created by the universe itself. This perspective not only deepens our understanding of physics, but also invites a sense of wonder and connectedness, reminding us that even in our most solitary moments, we are inextricably linked to the vast expanse of the cosmos. When Albert Einstein introduced his theory of general relativity in 1915, he fundamentally transformed the way we understand gravity. In this elegant framework, gravity is no longer a force acting at a distance, as Newton had described, but rather the manifestation of curved space-time shaped by mass and energy. Objects follow the straightest possible paths, or geodesics, within this curved geometry, producing the motions we observe in planets, stars, and galaxies. While general relativity has passed every experimental test with remarkable precision, scientists have continued to explore whether space-time might possess even more subtle geometric properties beyond curvature, opening the door to extensions such as Einstein-Cartan theory. Einstein-Cartan theory builds upon general relativity by incorporating an additional geometric property known as torsion. Whereas curvature bends space-time in response to mass and energy, torsion introduces a twisting of space-time, which can interact with the intrinsic angular momentum, or spin, of matter. This means that particles with spin, such as electrons and protons, could in principle influence the local geometry of space-time in ways that are invisible in classical general relativity. Torsion is subtle, producing effects that are exceedingly small under ordinary circumstances, but in extreme environments, near neutron stars, black holes, or during the earliest moments of the universe, it could play a meaningful role, potentially bridging the gap between general relativity and quantum mechanics. The mathematical foundation for torsion, and the broader geometric structures underpinning space-time, owes much to the work of the French mathematician Élie Cartan. In the early 20th century, Cartan developed a generalization of differential geometry, a mathematical language capable of describing both curvature and torsion. His contributions allowed physicists to formalize ideas about twisting spacetime and to explore how spin and mass might interrelate in a consistent geometric framework. By introducing the concept of a connection with torsion, Cartan provided a natural way to extend Einstein's elegant equations, revealing that spacetime is not merely a smooth, curved fabric, but a dynamic entity with richer geometric possibilities. In Einstein-Cartan theory, the fundamental equations that describe gravity resemble Einstein's original field equations, but with additional terms that account for the spin density of matter and the resulting torsion. While these equations are complex, they preserve the key insight of general relativity. Spacetime geometry dictates motion, and the distribution of mass and energy determines the shape of that geometry. Torsion adds an extra layer of subtlety, hinting that spinning matter does not merely move along curved paths, but can in turn influence the very twisting of the paths themselves. In this sense, the universe is more interactive than general relativity alone suggests, a cosmic dance in which geometry responds delicately to both mass and spin. This extension of general relativity also highlights a continuous thread from classical mechanics to modern geometric understanding. Newton provided the laws of motion and the gravitational force law, offering a powerful approximation that works beautifully in everyday life. Einstein replaced the force with curvature, revealing that the familiar attraction of objects arises from the underlying shape of spacetime. Cartan extended this picture further, showing that spacetime can twist as well as bend, particularly in the presence of spinning matter. Each step in this progression preserves the successes of its predecessors, while revealing additional layers of subtlety, allowing us to perceive gravity not as a simple pull, but as a complex dynamic property of the universe. To grasp this more concretely, consider a spinning neutron star, an object of immense density with a radius of roughly 10 kilometers and a mass exceeding that of our Sun. In the framework of general relativity, the star curves the surrounding spacetime strongly, producing the gravitational effects we would expect. Light bends around it, nearby matter accelerates toward it, and time itself slows in its vicinity. In Einstein-Cartan theory, the star's rotation contributes a tiny torsional twist to the surrounding spacetime. While these effects are extraordinarily small, they illustrate that spin and geometry are deeply interwoven, suggesting that gravity's behavior is richer and more nuanced than the classical or even purely relativistic perspective alone can convey. Mathematically, the presence of torsion modifies the connection used to define parallel transport and curvature in spacetime. While we need not delve into the full complexity of the tensor equations to appreciate the concept, it is worth noting that the torsion tensor encodes how spacetime twists in response to spin. This introduces corrections to the motion of spinning particles and could influence processes at the quantum scale. Researchers exploring quantum gravity, including loop quantum gravity, and other discrete models of spacetime, often consider torsion as a potentially important feature, bridging the macroscopic predictions of general relativity with the microscopic behaviors of matter. Even in more familiar contexts, the principles behind Einstein-Cartan theory can illuminate our understanding of the cosmos. Consider the early universe, moments after the Big Bang, when densities and energies were extreme. In such conditions, torsion may have influenced the behavior of matter and the evolution of spacetime itself, potentially leaving subtle imprints in the large-scale structure we observe today. While current observational evidence is limited, ongoing studies in cosmology high-energy astrophysics and particle physics continue to explore whether these tiny twists of space-time might have observable consequences. The universe, it seems, may retain the memory of both curvature and torsion, encoded in the motion of stars, the spin of particles, and the fabric of space-time itself. Cartan's ideas also remind us that the language we use to describe gravity shapes our perception of the universe. Differential geometry allows us to see not just forces acting at a distance, but a rich, interactive space-time where mass and spin communicate subtly with geometry. This perspective encourages a conceptual fluidity in which the universe is no longer a static stage but a dynamic medium responding to the content within it. Even as we move from Newton to Einstein to Cartan, the continuity is clear. Each framework extends our vision, preserving the truths of its predecessors while revealing new dimensions of reality. Through this lens, gravity becomes less a mysterious pull and more a conversation between matter and space-time, a dialogue in which curvature and torsion encode the influence of mass, energy, and spin. The universe, in Einstein-Cartan theory, is a living geometric entity, capable of bending, twisting, and shaping the motion of every object it contains. It is a profound reminder that the cosmos is not only larger than our immediate perception, but also more intricate, responsive, and elegant than we often imagine. In contemplating these ideas, we're invited to appreciate the depth of scientific imagination. Newton gave us motion, Einstein revealed curvature, and Cartan illuminated the possibility of torsion. Each contributes to a richer understanding of the cosmos, showing that gravity is not merely a force but a multifaceted property of space-time, shaped by mass, energy, and spin. In this serene reflection, we find not only scientific insight but also a quiet wonder, a sense of connection to the elegant geometry that governs the motion of everything, from the smallest particles to the most massive stars, and indeed to the very structure of the universe itself. Imagine for a moment that gravity, the force we experience every day, is not a fundamental pull at all. This is the bold and fascinating premise of emergent gravity, a concept introduced by the Dutch theoretical physicist Erik Verlinde in 2011. Verlinde proposed that gravity might arise not as a primary force, but as a consequence of the way information is stored and processed at the microscopic level of space-time. In this view, the motion of planets, the fall of an apple, and the curvature of light around massive objects are all emergent phenomena, much like the surface tension of water arises from the collective interactions of countless molecules. It is a profound shift in perspective, suggesting that the familiar pull of gravity is a macroscopic effect, a gentle echo of deeper underlying processes that remain invisible to our everyday senses. At the heart of Verlinde's proposal lies the concept of entropy, the measure of disorder, or the number of possible microscopic arrangements of a system. Just as thermodynamics links the macroscopic behavior of gases to the motions of individual molecules, emergent gravity seeks to connect the large-scale geometry of space-time to the information contained at microscopic scales. In this framework, mass and energy do not simply bend space-time as in Einstein's general relativity. They influence the distribution of information in a way that produces what we perceive as gravitational attraction. Objects move along paths that maximize entropy, responding to the underlying statistical tendencies of the universe rather than to a classical force. To explore this idea further, it is helpful to consider the holographic principle, a concept developed through the work of Leonard Susskind, Gerard 't Hooft, and later Juan Maldacena. The holographic principle suggests that all of the information contained within a volume of space can be represented as data encoded on the boundary of that space, much like a hologram projecting a three-dimensional image from a two-dimensional surface. In this view, the universe behaves in ways analogous to a holographic projection, where the large-scale geometry of space-time and the forces we perceive emerge from the informational content on its boundaries. Gravity, therefore, is intimately connected to information, entropy, and the microscopic structure of reality, rather than being an independent fundamental interaction. Verlin's emergent gravity offers an elegant explanation for phenomena that have puzzled astrophysicists for decades. Observations of galactic rotation curves, for instance, suggest that stars at the outer edges of galaxies move faster than Newtonian predictions would allow if only visible matter were present. Traditionally, this discrepancy has been attributed to dark matter, an invisible form of mass that exerts gravitational influence. Emergent gravity provides an alternative explanation. The apparent extra pull arises naturally from the way information and entropy are distributed in the spacetime surrounding the galaxy. While this theory does not yet replace dark matter entirely, it offers a compelling framework for understanding gravitational effects without invoking additional unseen matter, and it is actively tested through astronomical observations and surveys. The beauty of emergent gravity lies not only in its explanatory power, but also in the bridge it builds between classical, relativistic, and quantum perspectives. Newton's laws describe motion in a familiar macroscopic world. Einstein revealed that gravity is geometry, curving the very fabric of space-time. Emergent gravity goes further, suggesting that geometry itself and the motions we observe within it are consequences of statistical and informational principles at a deeper level. It invites us to consider that the universe is not only a collection of objects in space, but also a vast network of information, with gravity arising as a natural consequence of its internal organization. At a conceptual level, one can imagine the universe as a vast digital canvas, where bits of information encode the potential arrangements of space-time and matter. Each star, planet, and particle contributes to this intricate tapestry. The paths that objects follow are determined not by a mysterious pull, but by the collective tendency of the universe to maximize entropy and optimize the distribution of information. In other words, when a planet orbits a star, it is tracing a path dictated by the informational structure of the cosmos, a subtle interplay between microscopic states and macroscopic behavior. Experimental efforts are beginning to probe these ideas more directly. Astronomers are analyzing rotation curves of galaxies, the distribution of cosmic filaments, and gravitational lensing patterns to test whether predictions from emergent gravity align with reality. Groups such as the European Southern Observatory and teams using the Hubble Space Telescope have provided data that help evaluate the subtle differences between classical, relativistic, and emergent models. While the theory remains young, its ability to offer new perspectives on long-standing cosmic puzzles makes it a particularly exciting area of research. It is worth noting that emergent gravity does not discard the successes of general relativity or classical physics. Instead, it complements them, showing that what we experience as curvature and attraction is a natural outcome of deeper principles. In everyday life, the equations of Newton and Einstein remain extraordinarily accurate, guiding satellites, predicting eclipses, and explaining the motion of our planet around the Sun. Yet when we peer into the cosmos at the scale of galaxies or consider the underlying fabric of spacetime itself, emergent gravity provides an enriching perspective that unifies phenomena across scales. The connection to holography also hints at profound philosophical implications. If information encoded on boundaries can give rise to the forces and geometry we observe within, then the universe is fundamentally relational, interconnected, and perhaps more abstract than our senses suggest. Matter, energy, and even space itself may be secondary to the more fundamental informational structure, a framework that shapes the reality we inhabit. It is a subtle, elegant reminder that our intuitive notions of pull, weight, and motion are rooted in a deeper, less visible order. Emergent gravity also resonates with ideas in quantum theory, where the behavior of particles is governed not by deterministic paths, but by probabilities, entanglement, and information flow. The microscopic states of space-time and the entropic tendencies that drive motion are reminiscent of the principles underlying quantum mechanics. In this sense, emergent gravity acts as a conceptual bridge, linking the large-scale elegance of general relativity with the probabilistic informational subtleties of the quantum world. It suggests a universe that is both continuous and discrete, geometric and statistical, familiar and deeply surprising all at once. By contemplating emergent gravity, we are invited to see the cosmos from a fresh perspective. No longer is gravity merely a mysterious pull acting across empty space. It is the collective expression of countless microscopic interactions, the unfolding of entropy across the universe, and the natural outcome of a holographic, information-rich structure. Galaxies, stars, and planets move not because an invisible hand tugs at them, but because they are following the curves and flows dictated by the informational architecture of the cosmos. As we reflect on these ideas, a sense of serene wonder emerges. Gravity becomes a window into the underlying order of reality, a bridge between the tangible world of falling apples and the abstract domains of information, entropy, and holographic principles. We see that the universe is not only shaped by matter and energy, but also by the subtle, hidden structure that organizes them. In this quiet contemplation, the familiar becomes extraordinary, and the gentle pull we feel beneath our feet transforms into a reflection of the deep informational and entropic currents that govern the cosmos on every scale, from the tiniest particle to the most distant galaxy. As we journey deeper into the foundations of gravity, we arrive at the realm of quantum geometry, where space-time itself may not be smooth and continuous, but composed of tiny, discrete building blocks. This is the domain explored by loop quantum gravity, a theory developed primarily by the Italian physicist Carlo Rovelli and the American physicist Lee Smolin during the 1980s. Loop quantum gravity seeks to reconcile general relativity, which describes the smooth curvature of space-time, with the principles of quantum mechanics, which govern the behavior of matter and energy at the smallest scales. The core idea is striking. Space-time is quantized, made up of finite, indivisible units, much like matter is composed of atoms. To visualize this, imagine a fabric not as a continuous sheet, but as a network of interconnected loops, threads, and nodes, each representing a fundamental unit of space. These networks are known as spin networks. They form the microscopic scaffolding of the universe, and the connections between nodes encode geometric information, such as areas and volumes. Each loop carries a quantum of space, and the entire network evolves according to specific rules derive from the principles of quantum mechanics. The evolution of these spin networks over time gives rise to spin foam models, which can be thought of as the history of how space-time itself unfolds. Where a spin network describes space at a given moment, a spin foam depicts the dynamic process by which these networks change and interact, creating the geometry of space-time in 4 dimensions. In this framework, gravity is not a continuous force, transmitted smoothly across space, but an emergent property of these discrete structures, the curvature we observe at macroscopic scales, the gentle arcs traced by planets around stars or light bending near massive objects, arises from the collective behavior of countless loops and nodes at the quantum scale. It is as if the smooth curves described by Einstein are the large-scale manifestation of an intricate pixelated underlying geometry, a subtle mosaic that produces the elegant motions of the cosmos without requiring a force in the classical sense. Loop quantum gravity stands in contrast to string theory, another prominent approach to quantum gravity. While string theory posits that the fundamental constituents of the universe are tiny, vibrating strings embedded in higher dimensional space, loop quantum gravity focuses on the quantization of spacetime itself. Strings vibrate in a pre-existing spacetime, whereas in loop quantum gravity, spacetime is not a background stage but an emergent dynamic structure built from spin networks and spin foams. Both approaches seek to unify gravity with quantum mechanics, but they start from very different assumptions, offering complementary perspectives on the deep structure of reality. One of the remarkable aspects of loop quantum gravity is that it predicts the existence of discrete units of area and volume. The smallest possible areas and volumes are on the order of the Planck scale, approximately 10 to the minus 35 meters for length and 10 to the minus 95 cubic meters for volume. While these scales are unimaginably small and far beyond current experimental reach, they provide a conceptual foundation for understanding how the smooth space-time of general relativity emerges from a fundamentally granular fabric. The continuum we perceive from the curve of the Earth's horizon to the orbit of Jupiter is thus an emergent property arising from the collective structure of these quantum loops. Spin foam models allow physicists to explore not just static properties of spacetime, but how it evolves dynamically. Each node and connection can change according to quantum rules, producing a history of the universe in which geometry itself fluctuates and transforms. This dynamic perspective is essential for understanding phenomena such as black hole interiors, the early universe during the Planck epoch, and potential quantum corrections to classical gravitational predictions. The notion that spacetime has a history, a sequence of evolving states encoded in spin foams, elevates our understanding of gravity from a static curvature to a living quantum mechanical process. Experimental tests of loop quantum gravity remain challenging, largely because the Planck scale is so far removed from our observational reach. However, researchers are investigating potential indirect effects, such as tiny deviations in the propagation of light across cosmological distances or subtle modifications to the behavior of black holes. Observatories like the European Southern Observatory, as well as teams analyzing data from the Hubble Space Telescope and upcoming space missions, provide increasingly precise measurements that could one day shed light on the quantum structure of spacetime. Even in the absence of direct measurement, the theoretical consistency and elegance of loop quantum gravity make it a compelling framework for bridging the gap between quantum mechanics and general relativity. It is important to recognize that loop quantum gravity preserves the successes of Einstein's theory at macroscopic scales. The motion of planets, the curvature of light near stars, and the expansion of the universe are all accurately described by general relativity. Loop quantum gravity does not discard these predictions. Rather, it explains how such smooth curvature can emerge from an underlying discrete geometry. In this way, the theory provides continuity from classical mechanics to relativistic physics to the quantum domain, revealing a layered understanding of the universe in which each scale builds naturally upon the one beneath it. The interplay between spin networks, spin foams, and macroscopic curvature also offers profound philosophical implications. Space and time, once thought to be absolute and continuous, are revealed as emergent, relational, and inherently quantum. Gravity is no longer a force transmitted through empty space. It is a manifestation of the deep structure of reality, a statistical and geometric outcome of countless microscopic loops interacting according to precise quantum rules. The universe, in this light, is a dynamic, interconnected mosaic, with each part influencing and shaping the whole. As we consider this perspective, it becomes easier to reconcile the seeming paradoxes of modern physics. The deterministic paths of planets, the smooth geometry of space-time, and the probabilistic, fluctuating nature of quantum mechanics all find their place in a coherent picture. Loop quantum gravity offers a vision in which the macroscopic and microscopic, the continuous and discrete, coexist naturally, producing the familiar behavior of gravity as an emergent consequence of a rich quantum mechanical architecture. Through this lens, we begin to appreciate that gravity is not merely a pull between masses or a curvature imposed by large bodies, but a subtle quantized property of the universe itself. Each spin network, each spin foam, contributes to the emergence of the space-time fabric that guides stars, light, and planets alike. The universe is not a smooth stage with objects moving across it. It is a living, evolving structure, intricately woven from loops of quantum geometry. In this quiet reflection, we can sense the profound elegance of the cosmos, where the smallest units of space dictate the grand arcs of galaxies, and where understanding emerges not from forces alone but from the fundamental, discrete threads of reality that compose the very essence of space-time. Imagine a universe where gravity is not a force transmitted invisibly between masses, but a manifestation of deeper statistical principles, a thermodynamic consequence of space-time itself. This is the striking insight explored by the American physicist Ted Jacobson in 1995. Jacobson showed that Einstein's field equations, the very equations that describe how matter and energy curve space-time, can be derived from the principles of thermodynamics, the same laws that govern heat, energy, and entropy in everyday physical systems. In this perspective, the curvature of space-time and the motion of planets, stars, and galaxies is analogous to the behavior of molecules in a gas responding to temperature and pressure, with gravity emerging naturally as a statistical effect of underlying microstates. At the heart of this idea is the concept of space-time entropy. Just as a gas possesses entropy related to the number of ways its molecules can be arranged, space-time itself can be thought of as composed of fundamental atoms, discrete units whose arrangements encode geometric information. Each unit contributes to the total entropy of a region, and changes in these arrangements manifest as the curvature we associate with gravitational effects. Rather than being an imposed force, gravity becomes the statistical tendency of space-time to evolve toward configurations that maximize entropy. guiding the motion of matter along paths dictated by the underlying informational structure. Black holes provide a particularly vivid illustration of these principles. In the 1970s, Jacob Bekenstein and Stephen Hawking revealed that black holes possess entropy proportional to the area of their event horizons and emit a faint radiation, now known as Hawking radiation. The entropy of a black hole, remarkably, is not related to its volume but to its surface area, suggesting that the informational content of space-time is encoded at boundaries, a notion that foreshadows the holographic principle. These discoveries link gravity, thermodynamics, and information in a profound way. The dynamics of space-time, the behavior of matter, and the flow of energy are interconnected through fundamental statistical laws, much as the motion of air molecules governs the pressure we feel in a room. Jacobson's work shows that Einstein's equations themselves are equivalent to the thermodynamic relation heat equals temperature multiplied by the change in entropy, applied locally to space-time. In other words, the curvature of space-time is not imposed externally, but emerges naturally from thermodynamic reasoning. This realization unites geometric and statistical perspectives, suggesting that what we perceive as gravity is the macroscopic manifestation of countless microscopic degrees of freedom, each obeying simple quantum rules. Planets orbit stars not because they are being pulled, in the traditional sense, but because the underlying microstructure of space-time guides their paths along the contours of maximal entropy. The notion of atoms of space-time invites us to imagine a universe built from discrete fundamental building blocks, each contributing to the emergent phenomenon we call gravity. These units are unimaginably small, on the order of the Planck scale, roughly 10 to the minus 35 meters, and cannot be observed directly with current technology. Yet their collective behavior produces the smooth, continuous geometry described by general relativity. It is akin to a pixelated screen where individual pixels are imperceptible at a distance, but together they form a seamless image. In this case, the image is the elegant curvature of space-time guiding the motion of stars, light, and planets. Gravity, when understood thermodynamically, also provides a natural link between classical, relativistic, and emergent perspectives. Newton described the predictable motion of planets and falling apples through a universal force. Einstein revealed that this force is a geometric effect, the curvature of space-time shaped by mass and energy. Jacobson and other researchers extend this further, showing that this geometry itself may arise from the statistical mechanics of space-time's microscopic constituents. In this way, gravity becomes an emergent phenomenon, bridging the gap between the tangible motions we observe and the subtle, underlying processes at the quantum level. Experimental observations continue to support the connection between gravity and thermodynamics. Measurements of black hole radiation, the cosmic microwave background, and the large-scale structure of the universe provide insights into how space-time organizes itself, responding to energy, mass, and informational constraints. Institutions such as NASA, the European Space Agency, and observatories around the world contribute to this research, collecting data that help refine our understanding of the deep connection between curvature, entropy, and gravity. While much of the microscopic behavior remains theoretical, the macroscopic predictions of thermodynamic models align beautifully with known phenomena, reinforcing the validity of this perspective. Consider the subtle elegance of a planet orbiting a star. In Newtonian terms, it is pulled by a gravitational force proportional to the product of the two masses, and inversely proportional to the square of their separation. In Einsteinian terms, it follows a geodesic in curved space-time. In the thermodynamic view, that path emerges because the underlying microstructure of space-time arranges itself in such a way that entropy is maximized along that trajectory. The planet is not being tugged, nor is it merely following curvature. It is tracing the statistical imprint of space-time's microscopic degrees of freedom, a path dictated by the deepest principles of order and information. This framework also illuminates why gravity seems universal, yet remains weak compared to other fundamental interactions. The statistical nature of space-time implies that the cumulative effect of countless microscopic interactions produces a coherent large-scale behavior. Much as the pressure of a gas is the sum of innumerable molecular collisions, each microscopic contribution is tiny, but collectively they guide the motions of celestial bodies with exquisite precision. Gravity is simultaneously subtle and all-encompassing, emerging quietly from the vast informational network that underlies the cosmos. By viewing gravity through the lens of thermodynamics, we gain a perspective that unites emergent geometric and quantum ideas. Space-time is a dynamic, information-rich medium. Black holes reveal that entropy is encoded on surfaces, and planets, stars, and galaxies move as a natural consequence of the statistical tendencies of countless fundamental units. It is a universe in which order and geometry emerge from microphysical rules, a cosmos where gravity is less a force and more a reflection of the deep statistical structure that organizes reality itself. In this serene contemplation, one begins to see the universe as a harmonious self-organizing system where matter, energy, and geometry are inextricably linked through principles of entropy and thermodynamics. Gravity, far from being a simple tug, is the subtle statistical whisper of space-time's hidden architecture, guiding the motion of everything from the smallest particle to the largest galaxy. It is a quiet, profound reminder that the cosmos is not only vast but also elegantly interconnected, a tapestry woven from the deepest principles of physics and the intricate dance of information at the heart of reality. In the vast expanse of the cosmos, one of the most perplexing puzzles arises when we observe the rotation of galaxies. Stars at the edges of these immense spirals move much faster than expected based on the visible matter contained within them. According to Newtonian predictions, the gravitational pull from the observable stars, gas and dust, should be insufficient to keep these outer stars moving in such rapid, stable orbits. This discrepancy has long suggested the presence of unseen mass, the mysterious substance we call dark matter, thought to pervade galaxies and clusters alike. Yet some physicists have asked a bold question. What if the solution is not hidden matter, but a modification of gravity itself? This question led Mordechai Milgram, an Israeli physicist, to propose modified Newtonian dynamics, or MOND, in 1983. MOND posits that Newton's law of gravitation, which works beautifully for high accelerations such as those experienced on Earth or in the inner regions of galaxies, requires modification at extremely low accelerations, such as those found in the outskirts of galaxies. According to MOND, when the acceleration experienced by a star drops below a certain threshold, approximately 10 to the minus 10 meters per second squared, the effective gravitational pull transitions to a different behavior, producing stronger effects than Newton's law would predict. Remarkably, this simple adjustment can account for the flat rotation curves of galaxies without invoking dark matter, suggesting that gravity itself may behave differently at cosmic scales. Building on this foundation, Jacob Bekenstein, a Canadian physicist known for his pioneering work on black hole entropy, developed a relativistic extension of MOND called TeVeS, or Tensor Vector Scalar Gravity, in 1997. TeVeS preserves the successes of general relativity while incorporating modifications that replicate MOND-like behavior at galactic scales. The theory introduces additional fields, tensor, vector, and scalar, to the spacetime geometry, allowing it to accommodate the observed motions of stars while remaining consistent with relativistic phenomena, such as gravitational lensing. In essence, TeVeS bridges the gap between Newtonian intuition, relativistic accuracy, and the anomalous rotation curves that prompted these modifications in the first place. The motivation for these unconventional approaches is deeply observational. When Vera Rubin and her colleagues measured the rotation curves of dozens of spiral galaxies in the 1970s, they discovered that the stars at the outskirts moved at roughly the same velocity as those nearer the center, defying classical predictions. Similarly, Fritz Zwicky had earlier noted in the 1930s that galaxy clusters exhibited gravitational behavior that could not be explained by visible matter alone. These observations provide a compelling empirical basis for considering that either a large amount of unseen mass exists, or that the law of gravity itself changes under certain conditions. MOND and TeVeS explore the latter possibility, offering an alternative perspective on cosmic dynamics. It is important to understand that these modified gravity theories do not discard the successes of Newton or Einstein. Classical mechanics continues to describe the motion of objects in everyday life with exquisite accuracy, and general relativity explains gravitational lensing, time dilation, and the dynamics of strong gravitational fields. MOND and TeVeS are not replacements for these frameworks at familiar scales. They are extensions that address anomalies observed at extremely low accelerations and large cosmic distances. In this way, they highlight the adaptability and diversity of credible approaches to understanding gravity, showing that our theories are shaped by the scale and context of the phenomena we observe. One of the elegant aspects of MOND is that it predicts a very specific relationship between the baryonic, or visible, mass of a galaxy and the orbital velocities of its stars. This relationship, known as the baryonic Tully-Fisher relation, states that the total baryonic mass of a galaxy is proportional to the fourth power of the asymptotic rotational velocity. Observations across hundreds of galaxies remarkably confirm this pattern, suggesting that MOND captures a real underlying regularity of galactic dynamics. The simplicity of this prediction contrasts with the more complex assumptions required if one invokes dark matter, which must be distributed in just the right way to match observations. TeVeS adds further sophistication by allowing these modified dynamics to coexist with relativistic effects. For example, gravitational lensing, where light from distant galaxies bends around massive objects, can be accounted for in TeVeS without assuming dark matter halos. This ensures that the theory remains consistent with high-precision astronomical observations, such as those made by the Hubble Space Telescope and the Sloan Digital Sky Survey, which track both the motion of stars and the bending of light across vast cosmic distances. In this sense, TeVeS provides a unified framework in which modified gravity principles align with the relativistic phenomena we observe in the universe. The study of modified gravity also underscores the philosophical and methodological openness of science. Rather than assuming that the laws of physics we observe on Earth apply universally without adjustment, these theories consider that different scales may reveal new behaviors. Gravity, in this view, is not necessarily immutable. It may be emergent, scale-dependent, and sensitive to conditions that are rare in our local environment, but common across the cosmos. Researchers at institutions such as the Institute for Advanced Study in Princeton, the Perimeter Institute in Canada, and various observatories around the world continue to test these ideas, examining galaxy rotation curves, cosmic microwave background data, and the distribution of large-scale structures to evaluate the plausibility of MOND, TeVeS, and other modified gravity proposals. It is worth noting that while MOND and TeVeS provide compelling fits to galactic rotation curves, they do not yet address all phenomena attributed to dark matter, such as the detailed structure of galaxy clusters or the cosmic web observed in large-scale surveys. Nonetheless, these theories demonstrate that gravity may be more flexible and context-dependent than traditionally imagined. They encourage us to explore the boundaries of classical and relativistic mechanics, to consider that the universe may be teaching us about new principles, and to remain open to multiple theoretical frameworks that explain observational data. By examining these alternative models, we appreciate that gravity is not simply a monolithic force described once and for all by Newton or Einstein. It is a phenomenon whose behavior may change depending on the scale, the environment, and the distribution of matter. MOND and TeVeS illustrate the creative, evidence-driven ways in which physicists probe these limits, showing that even the most familiar forces in nature can surprise us. The universe, in this view, is a laboratory, and galaxies are experiments, revealing the subtle ways in which gravity may emerge, adapt, and manifest across cosmic distances. Through this exploration, we gain a deeper appreciation for the diversity of approaches in modern physics. Gravity is simultaneously well understood and mysterious, predictable and subtly complex. Modified gravity theories invite us to consider alternatives to dark matter, challenge assumptions about universal laws, and explore the remarkable interplay between observation, theory, and imagination. In the calm reflection of these ideas, we see the cosmos as a place of elegant surprises, where the familiar tug of gravity may have richer, more nuanced origins than we have long assumed, and where the pursuit of understanding reveals a universe more intricate and interconnected than ever before. In the silent stretches of the cosmos, space-time itself can ripple and vibrate, producing phenomena known as gravitational waves. Unlike light, sound, or electromagnetic waves, these waves do not require a medium. They are fluctuations in the very fabric of the universe, generated by the motion of massive objects. Imagine two black holes spiraling toward one another in a distant galaxy. As they dance ever closer, their immense masses warp space-time, sending ripples outward at the speed of light. These ripples stretch and compress space itself, minutely altering distances even across billions of kilometers. It is a subtle effect, yet one that carries profound information about the nature of gravity and the geometry of space-time. The first direct detection of gravitational waves came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, observed the merger of two black holes over 1 billion light-years away. This historic measurement confirmed a key prediction of Einstein's general relativity, providing not only a new window into the universe, but also a novel way of probing the dynamic geometry of space-time. Soon after, the European Virgo Observatory joined LIGO in collaborative measurements, enhancing sensitivity and improving the precision of source localization. Together, these observatories have since catalogued dozens of gravitational wave events, including neutron star mergers that illuminate the creation of heavy elements like gold and platinum. Each detection is a gentle whisper from the cosmos, offering a glimpse into the motions and masses of objects that would otherwise remain invisible. Gravitational waves are more than just confirmations of Einstein's predictions. They are experimental probes into the very structure of space-time. By measuring the amplitude, frequency, and polarization of these waves, scientists can test the predictions of general relativity in extreme conditions, far beyond the laboratory. Subtle deviations from expected waveforms might reveal corrections due to quantum gravity, emergent space-time effects, or alternative theories such as those proposed in modified gravity frameworks like MOND or TeVeS. Researchers like Eugenio Bianchi and Thomas Sotirio have explored the implications of gravitational waves in non-Riemannian geometries, investigating how torsion, spin, or additional fields could influence wave propagation. Their work illustrates that gravitational waves are not merely echoes of cataclysmic events, but tools to probe the deepest theoretical structures of the universe. Future missions promise to extend this observational reach even further. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will place highly sensitive detectors in space, free from the seismic noise that limits terrestrial observatories. By observing lower frequency waves produced by supermassive black holes and galactic binaries, LISA will explore a regime of gravity inaccessible from the ground. These observations could provide new tests of emergent gravity theories, offering insights into how space-time curvature arises from microscopic processes or information-theoretic principles. The combination of ground-based and space-based detectors will open a full symphony of gravitational phenomena, from rapid, high-frequency black hole mergers to the languid undulations of galaxy-scale systems. At a conceptual level, gravitational waves beautifully illustrate that gravity is not a force transmitted along invisible lines between masses. Instead, gravity is geometry in motion. The ripples we detect are distortions of the space-time fabric itself, and the objects that generate them follow paths dictated by the contours of that fabric. Light too follows these curves, producing phenomena such as gravitational lensing, while massive bodies like stars and planets trace geodesics along the warped space-time. In this sense, gravitational waves make visible the dynamism of geometry, providing a tangible connection between abstract theory and observable reality. The mathematics describing these waves, while intricate, can be captured conceptually in terms of how space-time intervals change over time. The strain, a dimensionless measure of the relative change in length, is exceedingly small, often on the order of 1 part in 10 to the minus 21. LIGO achieves sensitivity sufficient to detect changes smaller than 1,000th the diameter of a proton across kilometers of interferometer arms. This exquisite precision highlights not only human ingenuity, but also the subtlety of the phenomenon itself, revealing the delicate motion of space-time that underlies every gravitational interaction. Gravitational waves also connect naturally to emergent gravity ideas. In theories where space-time is an emergent phenomenon, arising from microscopic degrees of freedom or information-theoretic principles, the propagation of waves reflects collective behavior of these underlying elements. The ripples are not simply distortions of a pre-existing stage. They are dynamic manifestations of the emergent structure itself. Similarly, in modified gravity frameworks, gravitational waves offer a critical test of the behavior of space-time under conditions that deviate from classical expectations, potentially revealing small corrections to amplitude, speed, or polarization that distinguish one theory from another. The observational program is complemented by theoretical insights. Computational models simulate mergers of black holes, neutron stars, and other massive systems, predicting the waveforms that observatories should detect. These simulations incorporate general relativity's equations, quantum corrections, and in some cases modifications from alternative gravity theories. By comparing predicted waveforms to actual detections, scientists can refine models of mass, spin, orbital dynamics, and even test the possible existence of extra fields or non-standard spacetime properties. The collaboration between theorists and experimentalists exemplifies the ongoing dialogue between prediction and observation that lies at the heart of scientific discovery. In addition to probing exotic astrophysical events, gravitational waves deepen our understanding of the universe's history. Some waves carry signatures from the early universe, potentially from the inflationary period, revealing conditions a fraction of a second after the Big Bang. These primordial waves, though extremely faint, offer a unique window into physics at energy scales far beyond what any particle accelerator can achieve. Observatories like the planned Cosmic Explorer and upgrades to LIGO and Virgo aim to detect these relic waves, further connecting the geometry of spacetime to the evolution and structure of the cosmos. Through all of these perspectives, gravitational waves reinforce the central theme that gravity is not a conventional force. They are dynamic ripples in geometry, traveling across the cosmos, carrying information about the distribution of mass and energy, the motion of celestial bodies, and even the quantum or informational structure of spacetime itself. They invite us to observe gravity not as an invisible pull, but as a living, vibrating fabric, one that stretches, compresses, and flows in response to the cosmic dance of matter and energy. As we contemplate these gentle undulations across the universe, it is helpful to imagine spacetime as a vast, elastic ocean, with galaxies and black holes as swimmers whose movements create waves that propagate through the medium. Each detection, each subtle measurement, is a message from the universe, a confirmation that the geometry of spacetime is real, dynamic, and intimately connected to everything within it. Gravitational waves remind us that gravity is geometry in motion, a vibrant, livous aspect of reality, and that by listening carefully to these cosmic rhythms, we can gain insight into the deepest principles shaping the universe. Black holes are among the most fascinating and extreme objects in the universe, regions where space-time is curved to such an extent that the familiar rules of motion and gravity begin to break down. According to general relativity, a black hole forms when a massive object collapses under its own gravity to a point where the curvature of space-time becomes so steep that not even light can escape. The boundary beyond which escape is impossible is known as the event horizon, a one-way surface that marks the limit of causal influence. Crossing this threshold, an object can fall inward, but no signal, no particle, and no photon can return to the outside universe. It is a silent, invisible frontier, separating the known from the unknowable. At the very center lies the singularity, a point where the curvature of space-time theoretically becomes infinite, and classical physics ceases to provide meaningful predictions. While the singularity itself is hidden behind the event horizon, its existence has profound implications for our understanding of gravity and the fabric of the cosmos. The concept of the singularity was formalized through the pioneering work of Roger Penrose in the 1960s, who demonstrated that under general conditions, gravitational collapse inevitably leads to such points of extreme curvature. Penrose's theorems, alongside contributions from John Wheeler, who famously coined the term black hole in 1967, and Stephen Hawking, who explored their thermodynamic properties, provided a rigorous mathematical and physical foundation for these extraordinary objects. Observationally, black holes reveal themselves indirectly through their interactions with surrounding matter and light. Gas and dust falling toward a black hole form an accretion disk, heating to millions of degrees as gravitational energy is converted into radiation, producing X-rays and other emissions detectable across vast cosmic distances. The motion of stars orbiting invisible points, as seen in the center of our Milky Way galaxy, provides compelling evidence for a supermassive black hole weighing millions of times the mass of our Sun. These observations confirm the extreme curvature of spacetime predicted by Einstein's equations, and illustrate the limits of Newtonian intuition, which would predict catastrophic instability or unbounded motion rather than the stable orbits and emission patterns that astronomers observe. The geometry of space-time near a black hole is profoundly non-Euclidean. The usual notions of straight lines and flat planes no longer apply. Instead, geodesics bend dramatically, guiding particles and light along paths that appear counterintuitive from a classical perspective. Light that grazes near the event horizon can orbit multiple times before escaping, producing phenomena such as gravitational lensing and the eerie ring-like images captured by the Event Horizon Telescope. These observations are not only confirmations of general relativity, but also windows into the extreme behavior of matter and radiation under conditions far beyond anything encountered in ordinary life. Black holes also provide a unique laboratory for exploring the interplay between geometry and quantum effects. Stephen Hawking's theoretical prediction in 1974 that black holes emit a faint thermal radiation, now known as Hawking radiation, revealed that quantum processes near the event horizon could allow black holes to lose mass over vast timescales. This insight bridged gravitational physics, quantum mechanics, and thermodynamics, showing that black holes are not entirely inert, but dynamic entities whose existence reflects the deep interconnections of physical laws. The entropy of a black hole, proportional to the area of its event horizon rather than its volume, also reinforces the holographic principles discussed in earlier explorations, suggesting that information about the contents of a black hole may be encoded on its boundary. Extreme gravity near black holes illustrates the potential relevance of concepts like torsion and emergent spacetime. In regions of high curvature and high spin, the subtle twisting of spacetime described in Einstein-Cartan theory may become significant, influencing the motion of spinning particles and the structure of matter. Similarly, theories of emergent gravity imply that the curvature and dynamics near a black hole could reflect collective effects arising from microscopic degrees of freedom, where information and entropy play a critical role in shaping macroscopic geometry. While these effects are subtle and currently beyond direct observation, they highlight the conceptual richness of black holes as more than just endpoints of stellar evolution. They are laboratories for the deepest laws of physics. The behavior of matter and light near black holes also challenges our everyday intuitions. Time, for example, behaves differently near an event horizon. observers far from the black hole would see a clock approaching the horizon appear to slow, asymptotically freezing as it nears the boundary. For the object itself, however, time passes normally, and it crosses the horizon in a finite proper time. This illustrates the profound way in which space-time geometry governs motion and perception, showing that our classical sense of simultaneity and uniform time is only an approximation valid in weaker gravitational fields. Black holes vary widely in scale, from stellar mass black holes a few times the mass of the Sun to supermassive black holes weighing billions of solar masses at the centers of galaxies. Intermediate mass black holes, while harder to detect, may fill the gaps between these extremes, influencing the dynamics of globular clusters and dwarf galaxies. Each class demonstrates the universal nature of extreme curvature and the predictive power of general relativity, while offering opportunities to probe deviations from classical expectations, potential quantum corrections, and tests of alternative gravity theories. Gravitational waves, as discussed previously, provide another window into black holes. When two black holes merge, they create ripples in space-time that propagate outward, carrying information about their masses, spins, and orbital dynamics. The signals detected by LIGO and Virgo offer unprecedented tests of general relativity in the strongest possible gravitational fields, confirming the extreme curvature predicted by theory, while opening the possibility of detecting subtle corrections from torsion or emergent spacetime effects. Black holes thus connect multiple threads of modern physics, linking classical geometry, quantum mechanics, and observational cosmology in a single, astonishing phenomenon. In contemplating black holes, we also confront the profound limits of observation. The singularity lies hidden behind the event horizon, inaccessible to direct measurement, yet its existence is inferred from the behavior of surrounding matter and radiation. These objects remind us that gravity is not simply a force pulling objects together. It is a manifestation of geometry, a dynamic curvature of space-time shaped by mass, energy, and perhaps even spin and informational degrees of freedom. From the motion of distant stars to the bending of light around massive bodies, black holes reveal the universe's power to curve, twist, and shape itself in ways that challenge our intuition and expand our imagination. In the serene reflection upon black holes, we see a universe where gravity reaches its extremes, yet remains comprehensible through the language of geometry. The insights of Stephen Hawking, Roger Penrose, and John Wheeler illuminate the profound unity of physics, connecting the macroscopic behavior of stars and galaxies to the microscopic properties of space-time. Black holes are not merely cosmic curiosities. They are the ultimate demonstration that gravity is geometry in motion, a dynamic, interconnected property of the cosmos, revealing that the familiar tug we feel beneath our feet is but a gentle echo of the universe's extraordinary curvature. Gravity, as we've explored it so far, is often understood through the elegant language of geometry, curvature, and emergent phenomena. Yet the quest to reconcile this familiar picture with the strange probabilistic world of quantum mechanics has led physicists to attempt a description of gravity using the tools of quantum field theory. In this approach, gravity is envisioned as a particle-mediated interaction, much like electromagnetism is carried by photons. The hypothetical particle responsible for transmitting gravitational effects is called the graviton, a massless spin-2 particle that conveys the curvature of space-time in a quantized form, The concept of the graviton emerges naturally when one attempts to describe small perturbations in spacetime geometry as quantum fields. If the curvature caused by a massive object can ripple through spacetime, as we see with gravitational waves, then these ripples can be thought of as propagating particles, carrying energy and momentum across vast distances. This particle-based perspective allows physicists to apply familiar techniques from quantum field theory, using perturbative expansions to calculate interactions and predict effects at low energies. In the 1970s, Steven Weinberg explored this approach in detail, demonstrating that gravity can be treated consistently as a low-energy effective quantum field theory. Later, John Donoghue extended these ideas, showing that predictions for weak gravitational interactions, such as corrections to the Newtonian potential at large distances, can be computed with remarkable accuracy. These results provide a bridge between classical general relativity and the quantum world, offering insight into how gravity might behave under conditions where both curvature and quantum effects are significant. Despite these successes, the quantum field theory of gravity faces significant challenges, the most notorious of which is non-renormalizability. Unlike quantum electrodynamics or the other forces described by the Standard Model, the perturbative calculations of gravitational interactions produce infinities that cannot be removed by the usual renormalization techniques. This indicates that, at extremely high energies or extremely small scales near the Planck length, a new, deeper theory is required to describe gravitational phenomena. Researchers are actively exploring candidate theories, including string theory and loop quantum gravity, which seek to provide a self-consistent framework for gravity at all scales. Comparing the particle-based view of gravity with the geometric perspective offers a fascinating contrast. In general relativity, gravity arises from the curvature of spacetime, guiding the motion of objects along geodesics without invoking a force in the traditional sense. In the quantum field picture, gravitons act much like photons, transmitting gravitational influence across space. These are not contradictory views but complementary ones. One describes the macroscopic emergent behavior of space-time, while the other focuses on the underlying quantum structure that gives rise to that behavior. Both perspectives are essential for understanding gravity across scales, from the smooth arcs of planetary orbits to the quantum fluctuations that may dominate near singularities or in the earliest moments of the universe. The interplay between these approaches also illuminates the broader challenges of unification in physics. While quantum field theory has succeeded in describing 3 of the 4 fundamental forces, gravity remains uniquely stubborn, resisting straightforward quantization. This has led to innovative theoretical work, exploring whether spacetime itself might be emergent, as suggested in entropic gravity models, or whether the fundamental constituents of the universe are not points in space, but networks of relationships, as in loop quantum gravity. Gravitons, in this context, represent a useful conceptual bridge. They encode the way in which quantum fluctuations influence spacetime geometry, while maintaining continuity with macroscopic observations of curvature and motion. Experimental prospects for detecting gravitons directly are daunting, given their extraordinarily weak interactions. Nevertheless, indirect evidence emerges through phenomena such as gravitational wave propagation, quantum corrections to Newtonian potentials, and cosmological observations. For example, precision measurements of the cosmic microwave background or the behavior of light in strong gravitational fields may reveal subtle deviations from classical predictions, hinting at the quantum nature of gravity. These efforts are pursued by institutions such as the European Organization for Nuclear Research, NASA, and the Laser Interferometer Gravitational Wave Observatory, combining observational astrophysics with theoretical predictions to probe the deep structure of the cosmos. Conceptually, imagining gravity as both geometry and as a field of particles invites a new understanding of the universe. The large-scale curvature guides planets and stars, producing the elegant, predictable orbits we observe. At the same time, the underlying quantum fields may mediate interactions at the smallest scales, influencing the behavior of particles, black holes, and the early universe. This duality reflects a profound feature of nature. Phenomena that appear smooth and continuous at one scale may emerge from discrete, probabilistic processes at another. Gravity in this sense is both a river that flows visibly through the cosmos and a collection of ripples that carry subtle information at the quantum level. Even the smallest perturbations in space-time geometry can have profound consequences. Tiny fluctuations encoded in the quantum field of gravitons could have seeded the large-scale structure of the universe, influencing galaxy formation and the distribution of matter across billions of light years. These fluctuations may also contribute to the behavior of black hole horizons, the propagation of gravitational waves, and potentially the emergence of space-time itself from deeper, microscopic rules. Understanding these connections remains one of the most tantalizing challenges in modern physics, bridging the familiar motions of stars and planets with the intricate probabilistic fabric of quantum reality. By exploring gravity through the lens of quantum field theory, we gain insight into both its universal consistency and its underlying mysteries. We see how classical laws emerge from quantum principles, how particles like gravitons can carry curvature across space, and how the universe maintains coherence from the smallest scales to the largest. The complementary approaches of geometry and field theory provide a holistic view, showing that gravity is simultaneously an emergent property, a geometric deformation, and a quantum-mediated interaction. Each perspective enriches the other, offering layers of understanding that deepen our appreciation of the universe. In this reflective view, gravity is no longer confined to a simple pull between masses. It is a dynamic interplay of space-time curvature, quantum excitations, and statistical tendencies, bridging the observable cosmos with the underlying microphysical processes. The work of physicists like Steven Weinberg and John Donoghue demonstrates that even at low energies, where the familiar arcs of planetary motion dominate, quantum insights provide corrections and refinements, hinting at the profound structure beneath. Gravity is thus simultaneously tangible and subtle, classical and quantum, geometric and particulate, inviting us to contemplate the universe as a rich, interconnected tapestry woven from threads both visible and unseen. Gravity shapes the universe on every scale, from the arcs of planets around stars to the sprawling filaments of galaxies that stretch across hundreds of millions of light years. In cosmology, it is the sculptor of structure, guiding the formation of stars, galaxies, and clusters, and orchestrating the large-scale arrangement of matter throughout the cosmos. Without gravity, the universe would be a diffuse, featureless expanse, with matter drifting randomly through space. It is through the subtle pull of gravity that tiny fluctuations in the early universe grew into the rich tapestry of cosmic structures we observe today. Observational evidence for gravity's role in shaping the cosmos emerged slowly but compellingly. Fritz Zwicky in the 1930s studied the Coma Galaxy cluster and noticed that galaxies moved faster than expected given the visible mass. He inferred the presence of Dunkelmaterie or dark matter, an unseen component that exerts gravitational influence yet emits no light. Decades later, in the 1970s, Vera Rubin and her collaborators measured the rotation curves of spiral galaxies, finding that stars far from the galactic centers moved at speeds inconsistent with the distribution of visible matter. These pioneering studies demonstrated that the gravitational landscape of galaxies and clusters is not fully explained by ordinary matter, hinting at missing mass or perhaps deeper modifications to gravity itself. The existence of dark matter and dark energy raises profound questions about the nature of gravity at cosmic scales. Dark matter appears to provide the extra gravitational pull needed to explain the motions of stars and galaxies, while dark energy is inferred from the accelerating expansion of the universe, first observed in the late 1990s through the study of distant supernovae by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees. Both phenomena suggest that the universe is dominated by components that interact primarily through gravity, shaping the cosmos in ways that challenge our intuitive understanding. While general relativity provides a framework for interpreting these effects, the precise nature of dark matter and dark energy remains one of the central mysteries of modern physics. Alternative explanations have also been proposed. Modified gravity theories such as MOND and its relativistic extensions suggest that the laws governing gravitational interactions may change at very low accelerations or on large scales, potentially removing the need for dark matter. These theories attempt to reconcile observations of galactic rotation curves and cluster dynamics with a revised understanding of gravity, preserving the successes of general relativity in familiar contexts, while providing new predictive frameworks. The debate between unseen matter and modified gravity illustrates the scientific process at its best. Observations inspire models generate predictions, and evidence gradually clarifies which frameworks provide the most consistent explanation of reality. Gravity's influence is not confined to the grander scales. It connects directly to local phenomena in surprising ways. The same laws that govern the rotation of galaxies also dictate the orbit of the Earth around the Sun and the motion of satellites around our planet. The interplay between local and cosmic gravity allows astronomers to use familiar systems as laboratories for understanding the universe at large. For instance, measurements of the motion of stars within galaxies, gravitational lensing of distant quasars, and the cosmic microwave background radiation provide complementary perspectives on how gravity operates across vastly different scales, linking the intimate to the immense. Contemporary cosmologists continue to refine our understanding of cosmic scale gravity. Observatories such as the European Southern Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter/Submillimeter Array provide high-resolution data on galaxy distributions, supernova, and cosmic background radiation. Large-scale surveys, including the Sloan Digital Sky Survey and the upcoming Vera Rubin Observatory, map millions of galaxies across billions of light-years, offering statistical power to test models of dark matter, dark energy, and modified gravity. These observations reveal subtle patterns, such as the clustering of galaxies along filaments and the formation of cosmic voids, all of which reflect the guiding hand of gravity over eons. Gravity also connects intimately with the expansion of the universe. Observations of the redshift of distant galaxies show that space itself is stretching, carrying galaxies apart, Yet the rate of expansion is not uniform. It is influenced by the gravitational pull of matter and the repulsive effect attributed to dark energy. The interplay between these forces shapes the large-scale dynamics of the universe, influencing the formation of cosmic structures, the behavior of galaxy clusters, and the future evolution of the cosmos. Gravity, therefore, is both a sculptor and a moderator, balancing the growth of structures against the accelerated expansion of space. The richness of observational evidence reinforces the theoretical frameworks developed to explain cosmic phenomena. General relativity continues to provide the foundation for understanding large-scale gravitational effects, predicting phenomena such as gravitational lensing, the bending of light by massive clusters, and the dynamics of binary pulsars. At the same time, cosmologists explore whether additional physics is required to account for anomalies or subtle discrepancies, whether through new forms of matter, modifications to gravity, or emergent phenomena arising from the statistical behavior of space-time at large scales. Each new observation, from the rotation of distant galaxies to the structure of the cosmic microwave background, provides a critical test of these models. The connection between cosmic and local gravity is particularly elegant. Planetary orbits, satellite trajectories, and the motion of stars within the Milky Way all adhere to the same physical laws that govern the expansion and clustering of galaxies billions of light-years away. This unity demonstrates the universality of gravity, highlighting that whether we're considering the fall of an apple, the orbit of a planet, or the structure of a supercluster, the same principles apply, only manifesting differently depending on scale and context. In reflecting on cosmology, dark matter, and dark energy, we begin to see gravity not merely as a local force, but as a pervasive, organizing principle of the universe. It shapes structure, governs motion, and dictates the evolution of the cosmos, connecting the smallest scales to the largest in an intricate and harmonious web. Observations by Vera Rubin, Fritz Zwicky, and contemporary cosmologists provide the empirical foundation for these insights, while theoretical explorations continue to test, refine, and expand our understanding. Gravity in this cosmic context is both familiar and profoundly mysterious, guiding the universe with a gentle hand that stretches from the planets beneath our feet to the most distant galaxies at the edge of observability. Gravity, as we have explored, is often described through local interactions, the curvature of space-time, or emergent statistical effects. Yet in recent years, theorists have begun to consider a more subtle and far-reaching possibility, that gravity may have non-local aspects, intimately connected with the strange and counterintuitive phenomena of quantum entanglement. In non-local gravity frameworks, the behavior of matter and space-time in one region could, in principle, be influenced by distant regions in ways that go beyond the familiar, classical picture of forces propagating through space. This concept challenges our everyday intuitions while remaining grounded in rigorous mathematical and physical reasoning. A central insight linking non-local gravity to quantum mechanics comes from the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. This bold idea suggests a deep equivalence between two seemingly disparate phenomena, Einstein-Rosen bridges, or wormholes, and Einstein-Podolsky-Rosen entanglement, the quantum correlation between distant particles. In essence, ER equals EPR proposes that entangled particles may be connected by non-traversable wormholes at a fundamental level, such that the geometry of space-time itself encodes quantum informational relationships. While these wormholes cannot be used for faster-than-light communication, the conjecture hints at a profound unity between space-time geometry and the informational structure of the universe, suggesting that gravity and quantum entanglement are not independent but intimately intertwined. Non-local gravity frameworks explore the idea that the entanglement of fundamental degrees of freedom could give rise to gravitational effects, effectively producing curvature and motion as emergent consequences of information distribution. In these models, what we perceive as the gravitational pull of one mass on another may be a manifestation of correlations in a vast network of entangled quantum states. Space and time, rather than being fundamental backgrounds, emerge from the collective organization of information, and gravity reflects the geometric consequences of this organization. Such an approach extends and complements ideas we've encountered in emergent gravity, thermodynamic gravity, and holographic principles, uniting them with the uniquely quantum phenomenon of entanglement. While these concepts are highly abstract, they are not purely philosophical. Non-local aspects of gravity could, in principle, have observable consequences, particularly in extreme environments such as near black holes or during the early universe. The distribution of entanglement may influence the propagation of gravitational waves, the formation of horizons, or subtle correlations in cosmological structures. Although direct experimental tests remain beyond current technology, theoretical predictions guide observational strategies such as high-precision measurements of gravitational wave polarizations, the behavior of correlated particles in extreme gravitational fields, or the statistical patterns in the cosmic microwave background. Researchers at institutions including the Perimeter Institute, the Institute for Advanced Study, and the Kavli Institute for Theoretical Physics are exploring these possibilities, combining rigorous theoretical models with observational and experimental guidance. Non-local gravity also carries profound philosophical implications, challenging our intuitive notions of locality and causality. In classical physics, the influence of one object on another is transmitted through space over time, limited by the speed of light. Quantum entanglement, however, allows for correlations between distant systems that are established instantaneously, though without transmitting information in a classical sense. If gravity arises, at least in part, from such entanglement networks, then space-time itself becomes a manifestation of these correlations, and the universe reveals an interconnectedness that transcends our classical expectations. This is not mere speculation. It is logical extension of principles that have been repeatedly verified in quantum experiments, such as Bell tests, which confirm that entanglement is a fundamental property of nature. One can imagine a simplified analogy to help grasp these ideas. Consider a vast web of interconnected nodes, each representing a quantum degree of freedom. The pattern of connections, the strength of correlations, and the distribution of entanglement collectively determine the geometry of the web. Local perturbations, such as the addition of mass or energy, influence the pattern globally, reshaping the connections and producing what appears as a gravitational response. In this sense, gravity is non-local. The influence of one part of the system depends on the structure of the whole, encoded in the network of entangled states. The macroscopic curvature we observe, from orbiting planets to bending light, emerges naturally from this underlying web of information. Connections to holographic and emergent gravity perspectives reinforce the plausibility of non-local gravity. In holographic frameworks, The information content of a volume of space is encoded on its boundary, suggesting that local geometry is determined by global information. Similarly, emergent gravity models posit that macroscopic gravitational effects arise from the collective behavior of microscopic degrees of freedom. Non-local gravity extends these ideas, emphasizing that the relationships between distant degrees of freedom, entanglement across space, play a central role in producing the gravitational phenomena we observe. Experimental verification remains challenging, yet subtle effects may one day reveal the fingerprints of non-local interactions. For instance, gravitational wave measurements could detect small deviations from classical predictions due to entanglement-induced correlations. Likewise, tabletop experiments using quantum optical systems or ultra-cold atoms might provide analogues of spacetime networks, illustrating how entanglement can influence emergent geometry in controlled settings. Each new measurement helps constrain models and guides the refinement of our theoretical understanding, ensuring that non-local gravity remains firmly connected to empirical science. Through this lens, gravity appears not as a simple pull or a force acting through empty space, but as the emergent consequence of informational relationships woven into the fabric of reality. Space, time, and curvature are not fundamental givens. They arise from patterns of entanglement and correlation across the cosmos. The universe is a dynamic, interconnected system, where even distant regions are subtly linked through the hidden architecture of quantum information. Reflecting on non-local gravity and the ER equals EPR conjecture, we see a universe in which geometry and information are inseparable, and where entanglement provides a conceptual bridge between quantum mechanics and the emergent macroscopic laws of motion. Gravity is not merely local curvature, it is a manifestation of the deep global structure of the cosmos, encoded in the relationships between fundamental constituents. By considering these ideas, we expand our understanding of the universe, seeing it as a coherent, interconnected whole, where every part is subtly influenced by the structure of the entire informational network, and where the familiar experience of gravity is a visible reflection of these profound underlying connections. In the quiet confines of a laboratory, far removed from the vast reaches of the cosmos, physicists have found ways to explore the deepest principles of gravity using surprisingly tangible systems. One of the most remarkable approaches involves Bose-Einstein condensates, ultra-cold clouds of atoms cooled to temperatures near absolute zero, where quantum effects dominate and matter behaves as a single coherent entity. Within these condensates, researchers can create analogues of black holes and event horizons, allowing the study of phenomena that, in space, occur at scales and energies far beyond our reach. By observing the flow of atoms, phonons, or quasi-particles in these controlled environments, scientists gain insight into the behavior of space-time and gravitational effects in a manner that is both experimentally accessible and conceptually illuminating. The idea that complex gravitational phenomena could emerge from more fundamental systems draws inspiration from the work of Xiaogang Wen, a Chinese-American physicist who has studied condensed matter systems as analogues for emergent space-time. Wen demonstrated that collective behaviors in strongly correlated systems can give rise to emergent properties resembling the geometry of space and the dynamics of fields, suggesting that space-time itself might arise from the collective organization of microscopic degrees of freedom. Laboratory experiments inspired by these principles allow physicists to test predictions of emergent gravity in controlled conditions, observing how interactions at the smallest scales can produce macroscopic effects that mimic curvature, horizons, and other gravitational phenomena. In practical terms, analog gravity experiments often create conditions in which the speed of sound in the condensate varies across space, producing an effective horizon where phonons, quantum excitations analogous to particles of sound, cannot escape. These systems are analogues of black hole event horizons, and they allow the study of phenomena similar to Hawking radiation, where quantum fluctuations near a horizon generate particle emission. By measuring these emissions, researchers can probe the mechanisms through which emergent properties arise, exploring how microscopic rules and interactions give rise to phenomena that resemble gravitational curvature in the universe. Experiments conducted at institutions such as the Massachusetts Institute of Technology, the University of St. Andrews, and the University of Tokyo have successfully observed these effects, providing experimental support for concepts that were once purely theoretical. The insights gained from these laboratory analogues are profound. They show that curvature, horizons, and other gravitational phenomena do not necessarily require classical spacetime at the outset. Instead, such effects can emerge from collective interactions within a system governed by quantum mechanics and statistical principles. This bridges the gap between abstract theoretical models and empirical study, allowing researchers to test hypotheses about emergent gravity, space-time discreteness, and the role of information in shaping geometry. By observing how simple systems produce complex large-scale behaviors, we gain confidence that our understanding of cosmic-scale gravity can be informed by experiments conducted on a tabletop, a meter across rather than billions of light-years. The laboratory perspective also highlights the universality of emergent principles. Just as Bose-Einstein condensates can mimic horizons and curvature, other condensed matter systems, such as superfluids, graphene sheets, or optical lattices, can reproduce aspects of space-time geometry, topological defects, or wave propagation in curved spaces. Each of these analog systems allows physicists to explore different facets of gravity, from the behavior of horizons and information flow to the emergence of effective metrics and curvature. Together, they provide a rich experimental framework for studying principles that were previously confined to the realms of mathematics and theory. Emergent gravity models tested in the lab also offer a complement to astronomical observations. While telescopes and gravitational wave detectors reveal the behavior of stars, black holes, and galaxies, laboratory analogues provide a controlled environment in which parameters can be adjusted, measurements repeated, and subtle effects isolated. For example, by varying the interaction strength or density in a condensate, researchers can simulate how different distributions of mass or energy might influence spacetime curvature, testing predictions of thermodynamic gravity or holographic models. These experiments illuminate the connection between microscopic rules and macroscopic behavior, providing a conceptual bridge between theory and observation. In addition to testing theoretical models, analog systems help clarify the underlying mechanisms of gravity. They suggest that curvature and gravitational effects may arise naturally from the collective behavior of fundamental degrees of freedom, rather than from a fundamental force transmitted across space. This perspective reinforces the idea, explored in emergent gravity, thermodynamic gravity, and holographic principles, that space-time and gravity are phenomena that emerge from deeper informational, statistical, or quantum structures. By observing these effects in the lab, we gain a tangible sense of how the universe might organize itself at both microscopic and cosmic scales. The experiments also inspire new avenues of research and theoretical innovation. Laboratory analogues allow the exploration of non-trivial topologies, the effects of torsion or spin, and the dynamics of horizons in systems that are precisely controlled and well characterized. They provide a platform for studying how entanglement, correlations, and information flow can influence emergent geometry, complementing theoretical work on non-local gravity, ER equals EPR conjectures, and spin networks. In this sense, the lab becomes a microcosm of the universe, a place where the principles of cosmic gravity are reflected and explored under human-scale conditions. By linking these insights back to macroscopic cosmic gravity, we see that the same principles governing the flow of atoms in a condensate can illuminate the motion of planets, the curvature around black holes, and the dynamics of galaxies. The large-scale behavior of space-time, the bending of light, and the generation of gravitational waves all reflect patterns that emerge from the collective organization of more fundamental elements. Laboratory analogues, therefore, are not mere curiosities. They are essential tools for testing, visualizing, and understanding the deep principles that shape our universe. In contemplating these experiments, we begin to appreciate gravity as a dynamic, emergent phenomenon, one that is intimately connected to the behavior of matter, information, and collective interactions at all scales. The universe, both in the laboratory and in the cosmos, reveals a profound coherence in which microscopic rules give rise to macroscopic curvature, horizons, and gravitational behavior. Through analog systems, we glimpse the underlying architecture of reality, observing that the motions of atoms, quasi-particles, and waves echo the grand structure of space-time itself. These insights remind us that even the most abstract and high-level theories of gravity can be illuminated through careful, patient experimentation, revealing the elegant unity between the microcosm and the vast, stretching cosmos. Gravity, as we have explored, is deeply geometric, shaping the motion of stars, planets, and light through the curvature of space-time. Yet the standard Riemannian geometry of general relativity is not the only way to describe this curvature. Alternative geometrical frameworks, such as Finsler geometry and causal set theory, offer intriguing possibilities for extending our understanding of space, time, and gravitational phenomena. Finsler geometry generalizes Riemannian concepts by allowing the metric, the measure of distance in spacetime, to depend not only on position, but also on direction. This introduces an additional degree of freedom in how we describe curvature, opening new avenues for modeling an isotropic or direction-dependent gravitational effects that might manifest in subtle astrophysical observations. Causal set theory, developed in part by Raphael Sorkin, takes a different approach by proposing that spacetime is fundamentally discrete rather than continuous. In this framework, the fabric of the universe consists of a network of events, connected by causal relationships forming a partially ordered set. The familiar continuum of space and time emerges only as an approximation of these discrete elements at large scales. Causal set theory provides a way to reconcile general relativity with quantum mechanics by treating space-time itself as a collection of fundamental building blocks, each with causal connections, offering a new perspective on the emergence of curvature, horizons, and the propagation of gravitational influence. These alternative geometries also intersect naturally with the study of exotic topologies, such as wormholes and cosmic strings. Wormholes are hypothetical tunnels connecting distant regions of space-time, potentially allowing shortcuts across cosmic distances, though non-traversable under conventional physics. Cosmic strings, on the other hand, are one-dimensional topological defects that may have formed in the early universe, producing regions of concentrated curvature. Both concepts have observable implications. Light passing near a cosmic string could produce characteristic lensing effects, such as double images of distant galaxies, while wormholes would distort the propagation of light and gravitational waves in unique patterns. Observations of such phenomena could provide indirect evidence for the presence of these unusual topologies and for the validity of alternative geometric frameworks. The exploration of Finsler geometry and causal sets also connects to non-Riemannian concepts like torsion, which we discussed in the context of Einstein-Cartan theory. In non-Riemannian geometries, space-time may twist in addition to bending, influencing the behavior of spinning particles and potentially leaving subtle imprints in astrophysical observations. Similarly, emergent gravity models suggest that space-time curvature arises from underlying microphysical or informational degrees of freedom, implying that the geometry we observe is the macroscopic manifestation of deeper structures. Together, these approaches illustrate that gravity is fundamentally geometric, shaped by the structure of space-time itself, rather than a conventional force acting across empty space. Observational consequences of alternative geometries can be subtle but measurable. The propagation of light is particularly sensitive to the underlying structure of space-time. For example, direction-dependent metrics in Finsler geometry could induce tiny deviations in the speed or bending of light, depending on the orientation of the photon's path, potentially detectable with high-precision astrophysical instruments. Similarly, the discreteness of causal sets might introduce small fluctuations in gravitational wave signals or the arrival times of photons from distant sources. Modern observatories, including the Hubble Space Telescope, the Laser Interferometer Gravitational Wave Observatory, and the upcoming Vera Rubin Observatory, provide data with the sensitivity necessary to probe these subtle effects, offering a bridge between abstract mathematical frameworks and empirical science. These alternative frameworks also highlight the flexibility of gravity as a concept. Classical Newtonian physics portrays gravity as a force between masses, general relativity as curvature of a smooth manifold, and now Finsler and causal set approaches suggest that geometry itself may be direction-dependent or fundamentally discrete. Each perspective preserves key empirical predictions while offering new possibilities for understanding anomalies, extreme astrophysical environments, or the earliest moments of the universe. By considering multiple geometrical descriptions, we gain a more complete picture of gravity's richness and potential complexity, recognizing that our intuitive experience of a smooth, continuous space-time is only an approximation of a deeper, more intricate reality. Laboratory experiments, analog gravity models, and computational simulations further illuminate these ideas. By modeling wave propagation, horizons, and curvature in controlled settings, researchers can test how alternative geometries affect the behavior of matter and radiation. These studies help clarify the connections between microscopic structure, emergent phenomena, and the macroscopic curvature that governs planetary orbits, stellar motion, and galactic dynamics. The insights gained from these models reinforce the principle that gravity is not a simple push or pull, but a manifestation of geometric relationships encoded in the structure of space-time itself. The study of exotic topologies also has practical implications for cosmology and astrophysics. Cosmic strings, if they exist, could influence the distribution of matter in the early universe, contributing to the formation of large-scale structures like galaxy clusters and filaments. Wormhole geometries, while hypothetical, challenge our understanding of causality and connectivity in spacetime, inspiring theoretical work that may eventually inform quantum gravity or emergent spacetime models. Even if direct detection proves elusive, these concepts expand our conceptual toolkit, allowing physicists to explore the limits of general relativity and the range of possible gravitational behaviors. By integrating these alternative geometries with previous insights into torsion, emergent gravity, and quantum correlations, we see a coherent picture in which gravity arises as a property of the underlying space-time manifold. The specific rules, whether continuous or discrete, isotropic or direction-dependent, smooth or twisted, determine how matter moves, how light propagates, and how cosmic structures form. This perspective reinforces the view that gravity is fundamentally geometric, and that the rich diversity of mathematical frameworks reflects the potential subtlety and complexity of the universe itself. Ultimately, Finsler geometry, causal set theory, and exotic topologies remind us that the familiar curvature described by Einstein is only one aspect of a larger landscape of possible spacetimes. Gravity, in all its manifestations, is a reflection of the structure, connectivity, and topology of the cosmos. From the twisting of non-Riemannian spacetime to the discrete events of causal sets and the subtle signatures of cosmic strings or wormholes, the universe demonstrates that geometry, in its many forms, governs motion, interaction, and the very fabric of reality. By embracing these alternative perspectives, we deepen our understanding of gravity, appreciating it not as a conventional force but as a dynamic, richly structured property of spacetime itself. Pushing the boundaries of our understanding of gravity requires more than theory. It demands precise, careful experiments that test the limits of general relativity and explore unconventional possibilities. One such endeavour is the Microscope mission, launched by the French space agency CNES in 2016. This satellite was designed to test the weak equivalence principle with unprecedented precision, comparing the free fall of two test masses of different compositions in orbit around Earth. By measuring accelerations to 1 part in 10 to the 15th, Microscope confirmed that, to extraordinary accuracy, all bodies fall at the same rate regardless of their internal structure or composition. These results not only reinforce general relativity, but also provide stringent constraints on alternative theories of gravity, including certain scalar tensor models and emergent gravity frameworks. Complementing large-scale missions, laboratory experiments on Earth have become increasingly sophisticated. Cold atom interferometry, for instance, uses clouds of ultra-cold atoms cooled to near absolute zero, manipulating their wave-like nature to measure tiny gravitational effects with extraordinary precision. By splitting and recombining atomic wave packets in a controlled environment, physicists can detect minuscule differences in acceleration, testing for deviations from Newtonian predictions or general relativity. Experiments conducted at institutions such as the University of Vienna, Stanford University, and the National Institute of Standards and Technology have demonstrated sensitivities capable of probing gravitational effects at scales previously inaccessible, potentially revealing the influence of hypothetical particles, non-local interactions, or quantum corrections to gravity. Tabletop experiments like these provide unique insight into regimes where conventional astronomy cannot easily reach. Unlike distant galaxies or black holes, laboratory systems offer controlled, repeatable conditions, allowing physicists to isolate specific variables and test precise predictions. For example, variations in the inverse square law at millimeter or submillimeter scales, predicted by some modified gravity theories, can be explored using torsion pendulums or microcantilevers, while Bose-Einstein condensates and optical lattices can simulate emergent space-time effects, revealing how microscopic interactions might produce macroscopic curvature. These experiments connect the abstract ideas of emergent gravity, causal set theory, and torsion-based models to concrete, measurable phenomena. Precision astrophysics also plays a critical role in validating theoretical models. Observations of pulses in binary systems, the timing of millisecond pulses, and the tracking of spacecraft within the solar system provide data with extraordinary temporal and spatial resolution. The orbits of Mercury and other planets, measured over decades, confirm the predictions of general relativity to high precision, while anomalies or subtle deviations could hint at new physics. Similarly, observations of gravitational lensing, galaxy rotation curves, and the dynamics of clusters help constrain or support modified gravity and emergent frameworks, linking cosmological scale phenomena to terrestrial measurements. The interplay between theory and observation is continuous and essential. Experimental evidence informs theoretical models, which in turn guide the design of new experiments. For example, limits on equivalence principle violations derived from microscope influence the parameter space explored in cold atom experiments, while laboratory results help refine predictions for astrophysical phenomena such as the behavior of stars near supermassive black holes. This feedback loop ensures that gravity research remains both rigorous and imaginative, allowing science to explore extreme and subtle regimes without straying from empirical foundations. Experimental frontiers also include tests of gravitational wave propagation, exploring whether modifications to general relativity affect speed, polarization, or dispersion. LIGO and Virgo, along with future detectors like LISA, offer extraordinary precision, detecting space-time ripples from merging black holes and neutron stars. These observations provide indirect tests of emergent non-local or quantum gravity models, probing how space-time behaves under extreme curvature and energy density. When combined with tabletop measurements and orbital missions, these studies create a comprehensive, multi-scale map of gravitational behavior, linking the microscopic to the cosmic. Laboratory experiments further explore quantum aspects of gravity. Proposals using superconducting circuits, optomechanical systems, and ultrasensitive torsion balances aim to detect interactions between quantum states and gravitational fields, testing whether gravity itself exhibits quantized behavior or emergent properties. While the effects are subtle, the precision achievable in modern laboratories makes it possible to explore regimes where theoretical predictions diverge, offering potential insights into the connection between geometry, quantum mechanics, and information. These experimental approaches underscore a central lesson. Gravity cannot be fully understood from equations alone. It must be interrogated through careful measurement, whether by monitoring the motion of planets, detecting waves across billions of light years, or observing atoms in a cooled vacuum chamber. Each method provides complementary information, confirming familiar principles while testing the boundaries of theoretical innovation. The ability to connect observations at diverse scales, microscopic laboratory experiments, solar system dynamics, and extragalactic astronomy ensures that our understanding of gravity remains grounded in reality while exploring the possibilities suggested by modern theory. As we consider the experimental frontiers, it becomes clear that gravity is not a static, fully solved problem. It is a dynamic, continually tested feature of the universe whose laws are probed with ever-increasing precision. Microscope, cold atom interferometry, precision astrophysics, and gravitational wave observatories together form a network of empirical exploration, allowing physicists to test, constrain, and refine models ranging from general relativity to emergent gravity, modified Newtonian dynamics, and quantum gravity frameworks. The synergy between observation and theory highlights the richness of scientific inquiry, showing that gravity, far from being a simple or final concept, is a vibrant field of discovery spanning laboratories, telescopes, and the vast expanse of the cosmos. Ultimately, the experimental frontier reminds us that gravity, whether considered as curvature, a force, an emergent phenomenon, or a quantized interaction, is a tangible aspect of reality. Its principles are tested, measured, and validated across multiple scales, connecting the smallest laboratory systems to the most distant galaxies. Through these investigations, we gain both practical understanding and profound insight into the structure of space-time, the interplay of forces, and the subtle ways in which the universe organizes itself. Each experiment, whether on a tabletop or in orbit, is a step toward revealing the intricate, elegant architecture that underlies the gravitational phenomena shaping our cosmos. From the falling apple that inspired Isaac Newton to the warped horizons of black holes observed by the Event Horizon Telescope, gravity has always invited us to look deeper, to question what we think we know about motion, space, and time. Newton described gravity as a force acting at a distance, pulling objects together in ways that could be calculated with remarkable precision. His law of universal gravitation, with its elegant inverse-square relationship, provides the foundation for understanding planetary motion, tides, and orbital mechanics. Yet even in Newton's time, thinkers like Ernst Mach questioned the absoluteness of space, hinting that motion and inertia might be relational, influenced by the entire cosmos. This early philosophical insight foreshadowed the more radical reconceptualizations that would come with Einstein. Albert Einstein transformed our understanding of gravity with general relativity, recasting it not as a force but as the curvature of space-time. Mass and energy bend the fabric of the universe, and objects follow paths dictated by this geometry, tracing geodesics rather than responding to a pull. The equivalence principle, inspired in part by Machian ideas, ensures that free-falling objects experience no local gravitational force, while curvature produces tidal effects and the orbiting of planets. Observations of light bending around the sun, time dilation near massive objects, and the precise motion of Mercury's perihelion all confirmed Einstein's vision, showing that gravity is best understood as geometry, not as a conventional force. Building upon this foundation, 20th and 21st century physicists explored ever more subtle aspects of space-time. Élie Cartan introduced the concept of torsion, allowing space-time to twist as well as bend, providing a geometric framework in which spinning matter could influence the local structure of the universe. Later, researchers like Carlo Rovelli and Lee Smolin developed loop quantum gravity, describing space-time as composed of discrete spin networks and spin foams, where geometry itself is quantized. These ideas illustrate that what we perceive as continuous curvature emerges from an underlying granular structure, linking microscopic degrees of freedom to macroscopic phenomena. At the same time, emergent and thermodynamic perspectives offered complementary insights. Eric Verlinder's emergent gravity suggests that the familiar pull of gravity arises from entropic principles and information distribution, while Ted Jacobson showed that Einstein's equations could be derived from thermodynamic reasoning. Gravity, in these views, emerges from the collective behavior of microscopic constituents, whether atoms of spacetime, entangled quantum systems, or informational degrees of freedom. Black hole thermodynamics, with Bekenstein-Hawking entropy and Hawking radiation, further illustrates that gravitational phenomena are deeply connected to statistical mechanics and information theory, linking geometric curvature with microscopic behavior. Modified gravity theories, including Mond and Tevez, remind us that observation drives innovation. Discrepancies in galactic rotation curves, first noted by Fritz Zwicky and later meticulously measured by Vera Rubin, inspired alternative models that adjust gravitational laws at low accelerations or large scales. Laboratory experiments, from cold atom interferometry to microscope, provide precision tests of these ideas, while gravitational wave observatories like LIGO and Virgo confirm the dynamic curvature of spacetime under extreme conditions. Together, these approaches form a continuum from classical mechanics to cutting-edge experimental physics, demonstrating the interplay between theory, observation, and conceptual innovation. Non-local and quantum perspectives further expand our understanding. The ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind links entanglement and spacetime geometry, suggesting that correlations between distant quantum systems might manifest as subtle aspects of gravitational behavior. Laboratory analogues, such as Bose-Einstein condensates simulating horizons or curvature, allow physicists to test emergent gravity concepts in controlled settings, bridging abstract theory and tangible experiment. Alternative geometries, including Finsler metrics and causal sets developed by Raphael Sorkin, explore how direction-dependent distances or discrete causal structures might produce observable effects on light propagation and astrophysical phenomena. Each framework reinforces the idea that gravity is fundamentally a property of space-time, shaped by geometry, topology, and information, rather than a simple force acting between masses. Reflecting on the contributions of scientists both widely known and less mainstream, we see a rich tapestry of intellectual effort. From Isaac Newton and Albert Einstein to Elie Cartan, Mordechai Milgrom, Bruno Bertotti, John Donoghue, Xiaogang Wen, and countless others, the exploration of gravity spans philosophy, mathematics, observation, and experimentation. Each contribution adds nuance, highlighting different aspects of the phenomenon: local motion, cosmic structure, quantum emergence, or information theoretic underpinnings. The result is a multi-layered understanding in which gravity is simultaneously classical, relativistic, thermodynamic, quantum, emergent, and potentially non-local. Through this continuum, one principle stands out. Gravity is not a simple tug or push. It is a conceptual lens through which we perceive the universe, revealing the interconnections between matter, energy, space-time, and information. Planets orbit stars along geodesic shaped by the curvature of space-time. Photons bend around massive objects. Black holes radiate due to quantum effects, and the largest cosmic structures emerge from subtle fluctuations and interactions. Observations from the laboratory, orbiting satellites, ground-based telescopes, and gravitational wave detectors collectively affirm that gravity is a geometric, dynamic, and information-rich phenomenon connecting the microscopic to the cosmic. As we reflect on the journey from Newtonian intuition to the frontiers of quantum and emergent gravity, it is striking how each layer builds upon the previous, preserving the accuracy of classical predictions while revealing new depths and subtleties. Gravity is both familiar and profoundly mysterious, a property of the universe that shapes our daily experience while pointing toward the deepest principles of reality. It teaches us that space, time, and motion are interwoven in intricate ways, and that understanding emerges from observing patterns, testing ideas, and imagining possibilities within the rigorous constraints of mathematics and experiment. In the calm contemplation of gravity, we're invited to see the universe differently. The familiar pull beneath our feet is a reflection of a vast interconnected web of geometry, information, and motion. Stars, galaxies, black holes, and the cosmic microwave background are all threads in this tapestry, revealing the elegant principles that govern reality. The continuum from Newton to Einstein to modern emergent quantum and alternative theories provides a lens through which we can perceive both order and mystery, simplicity and complexity, continuity and discreteness. Ultimately, gravity serves as a conceptual lens, guiding our understanding of the cosmos and inspiring curiosity, wonder, and awe. It is a phenomenon that connects the smallest quantum fluctuations to the vast dance of galaxies, linking mathematics, observation, and experiment in a coherent and deeply satisfying narrative. By studying gravity, we not only understand the motions of objects and the structure of space-time, but also glimpse the profound, hidden architecture of the universe itself. It is a reminder that even the most familiar forces and motions carry the imprint of extraordinary principles, and that curiosity, careful observation, and imaginative thinking allow us to appreciate the elegant complexity of the cosmos in which we live.